The universe has always whispered its secrets in ways we're only beginning to understand. Picture this, floating through the infinite darkness of space, surrounded by silence, until suddenly a signal pierces the void. Not just any signal, but something strange, unexpected, as if the cosmos itself is reaching out. What if I told you that over the years, scientists have detected not one or two, but 25 of these enigmatic signals, each one a puzzle begging to be solved? These aren't just random blips on a radar, they're cosmic mysteries that defy our current understanding of physics, hinting at phenomena so extraordinary they might rewrite what we know about the universe itself. Think about the last time you looked up at the night sky and felt that tug of wonder. Now imagine discovering something up there that no one can fully explain, a signal that arrives with no clear source, no obvious explanation, just a fleeting burst of energy that leaves astronomers scratching their heads. Some of these signals repeat like a distant drumbeat from the depths of space, while others vanish as quickly as they appear, leaving behind more questions than answers. Are they messages from advanced civilizations, the echoes of collapsing stars, or something even stranger, something we haven't even dreamed of yet? The truth is, every time we detect one of these signals, it's a humbling reminder of how much we still don't know about the cosmos we call home. This is the story of those 25 mysterious signals, each one a clue in the greatest detective story ever told, with the universe itself as both the culprit and the witness. From bizarre radio waves that shouldn't exist to pulses of energy that travel farther than we thought possible, these signals challenge everything we thought we knew about space. And here's the most thrilling part. With every new discovery, we're not just uncovering the secrets of the universe, we're uncovering the limits of our own imagination. So settle in, because by the time we're done, you'll never look at the night sky the same way again. The cosmos is speaking. Are you ready to listen? The first signal on our list is the one that started it all, the wow signal, a burst of radio waves so extraordinary that the astronomer who discovered it scribbled, "Wow," right on the printout, giving it a name as unforgettable as the mystery itself. It was August 15, 1977, when a radio telescope in Ohio picked up something utterly bizarre, a strong, narrowband signal coming from the direction of the constellation Sagittarius, lasting for 72 seconds before vanishing without a trace. What made it so unusual? It hit a frequency of 1,420 MHz, a range where cosmic noise is minimal, and human interference is rare, almost as if someone had deliberately chosen the perfect channel to shout into the void. Scientists have spent decades trying to explain it. Some say it could have been a passing comet, but no known comet was in that region of the sky at the time. Others suggest it might have been a natural astrophysical phenomenon, like a pulsar or a quasar, but none match the signal's precise characteristics. And then, of course, there's the tantalizing possibility. What if it was artificial? What if, just for 72 seconds, we intercepted a transmission not meant for us? The signal was never detected again, despite repeated searches, making it the ultimate cosmic one-hit wonder. What's fascinating is how this single blip changed everything. Before WOW, most scientists dismissed the idea of searching for extraterrestrial signals as science fiction. But after, it became a rallying cry for SETI, the search for extraterrestrial intelligence, proving that sometimes the universe sends us a mystery so compelling we can't ignore it. Even today, with all our advanced technology, we still can't say for certain what caused that signal. Was it a fluke, a cosmic prank, or something far more profound? One thing's for sure, when the universe speaks, even if just for a moment, we do well to listen. The WOW signal didn't just fade into cosmic static. It left behind a legacy that continues to spark debate, inspire searches, and even shape how we think about our place in the universe. Despite countless attempts to catch it again, the signal remains stubbornly silent. as if the universe handed us a single, cryptic postcard and then refused to send another. Over the years, telescopes have scanned the same patch of sky, using technology far more advanced than what was available in 1977, yet nothing has ever matched its intensity or clarity. This absence is as baffling as the signal itself. Why would something so powerful only happen once? Theories about its origin have evolved, but none have fully cracked the mystery. Some researchers argue it could have been an incredibly rare natural event, like a burst of plasma from a distant star behaving in ways we don't yet understand. Others point to the possibility of Earth-based interference, though no man-made source has ever been identified that fits the signal's unique profile. Then there's the more provocative idea that it was a deliberate transmission, perhaps from a civilization far beyond our own, briefly turning its spotlight in our direction before moving on. Imagine the implications. If it was artificial, what does it say that we've never heard it again? Was it a distress call, a hello, or just a cosmic accident we misinterpreted? Culturally, the WOW signal has become more than just a scientific curiosity. It's a symbol of humanity's longing for connection in a vast, seemingly empty universe. It's appeared in documentaries, inspired novels, and even fueled conspiracy theories. For skeptics, it's a cautionary tale about jumping to conclusions. But for believers, it's proof that we're not just shouting into the void, that somewhere out there, something might be listening. The signal's enduring mystery has even influenced funding for SETI and similar projects, reminding us that sometimes the most important discoveries aren't answers, but questions that push us to look harder. Think about it. In 72 seconds, the WOW signal did what decades of speculation couldn't. It made the search for extraterrestrial intelligence feel urgent, tangible, real. And while we may never know what caused it, that uncertainty is part of its power. It's a reminder that the universe is full of surprises, and that the next great discovery might be lurking in the next burst of static, the next blip on a screen. So the search goes on, not just for a repeat of that famous signal, but for all the other wonders waiting to be found. After all, if the cosmos spoke once, who's to say it won't speak again? Fast radio bursts are like the universe playing a cosmic game of peekaboo, blinking into existence for mere milliseconds, then vanishing before we can fully grasp what we've just witnessed. These intense flashes of radio waves pack more energy than the sun emits in decades, yet they last shorter than the blink of an eye. The first one was discovered in 2007, buried in old telescope data like a hidden treasure, and since then, hundreds more have been detected, each one a fleeting enigma that defies easy explanation. What makes FRBs so baffling isn't just their brevity, it's their unpredictability. Most appear once and never repeat, like a firework exploding in the distant darkness. But then there's FRB 121102, the rebel of the group. Unlike its one and done counterparts, this one sends out bursts over and over, as if it's tapping out a message in celestial Morse code. Tracing its origin led scientists to a tiny galaxy 3 billion light-years away, home to an incredibly powerful magnetic star. Could these bursts be the death throes of collapsing neutron stars? The screams of black holes, or something even more exotic like cosmic strings vibrating through space-time. The real twist, some FRBs seem to come from our own cosmic backyard. In 2020, astronomers detected one originating inside the Milky Way, linking it to a known magnetar, a highly magnetic neutron star. This was a breakthrough, suggesting at least some FRBs stem from these extreme objects. But here's the catch: magnetars can't explain all FRBs, especially the ones from distant galaxies. The repeating bursts like 121102 don't fit neatly into any box. Their patterns are irregular, their energies inconsistent, almost as if multiple cosmic phenomena are masquerading under the same name. Imagine standing in a pitch-black forest, hearing twigs snap around you. Some sounds come from birds, others from falling branches, but a few make no sense at all. That's the puzzle of FRBs. With every new detection, the mystery deepens. Are we witnessing the birth of new astrophysics, or simply scratching the surface of something far grander? One thing's certain: these millisecond flashes are rewriting the rules, proving that even the briefest signals can hold the weight of the universe's biggest secrets. When it comes to fast radio bursts, the universe seems determined to keep us guessing. Scientists have thrown every possible explanation at these fleeting cosmic flashes, but each new discovery only adds more layers to the puzzle. One leading theory points to magnetars, those wildly magnetic neutron stars spinning like cosmic tops. Picture a celestial powerhouse with a magnetic field so intense it could strip the data from your credit card halfway across the galaxy. When these unstable beasts experience starquakes, their crusts crack open, releasing tsunamis of energy that might explain some FRBs. The detection of an FRB from a known magnetar in our own galaxy in 2020 seemed to confirm this until researchers realized these local bursts were far weaker than their distant cousins. Then there's the cosmic cataclysm camp, where neutron stars collide in spectacular mergers. Imagine two city-sized objects, each denser than a mountain, spiraling toward each other at nearly light speed before smashing together in an explosion so violent it warps space-time itself. These collisions could launch shockwaves powerful enough to produce FRBs, but there's a catch. Most FRBs don't line up with known merger events, leaving scientists scratching their heads. For those who love wilder possibilities, there's the alien megastructure hypothesis, the idea that advanced civilizations might be using focused energy beams to power interstellar ships or communicate across galaxies. While it's a tantalizing thought, most astronomers treat this as a last resort explanation. After all, as one researcher put it, when you hear hoofbeats, think horses, not unicorns. Still, the repeating FRBs with their erratic patterns keep this fringe theory alive, if only as a reminder of how much we don't know. The real breakthrough came when scientists started sorting FRBs into two distinct categories: repeaters and non-repeaters. This simple division hinted that multiple phenomena might be at play, like realizing some lightning strikes come from storms, while others erupt from volcanoes. By studying the way these bursts disperse their radio waves, researchers can now trace some back to their host galaxies, revealing clues about the environments that birthed them. Some FRBs originate in turbulent young galaxies packed with star formation, while others come from quieter, older neighborhoods, suggesting no single mechanism can explain them all. What's truly remarkable is how technology is rising to the challenge. New telescopes like CHIME in Canada scan the entire sky daily, catching FRBs in real time, while AI sifts through mountains of data for hidden patterns. With every detection, the mystery becomes both clearer and more complex, like assembling a jigsaw puzzle where new pieces keep changing shape. Whether they're cosmic accidents, stellar death cries, or something beyond our current physics, FRBs remind us that the universe still holds cards close to its chest. And that's what makes them so thrilling, not just the answers they might provide, but the questions they force us to ask. Long before fast radio bursts became cosmic celebrities, there was one that slipped into history almost unnoticed: the Lorimer burst. Detected in 2007 by astronomer Duncan Lorimer and his student David Narkevic, this brief blip of radio waves was hiding in plain sight, buried under 17 hours of archived data from the Parkes Radio Telescope in Australia. What made it extraordinary wasn't just its intensity. It carried the energy of 500 million suns, but the fact that it seemed to come from nowhere. Lasting just 5 milliseconds, it vanished as quickly as it appeared, leaving behind a trail of skepticism. Many dismissed it as telescope glitch, a cosmic hiccup too strange to be real. The burst's cosmic origins weren't confirmed until years later, and for good reason. Its dispersion measure, a clue tied to how much material the signal had traveled through, pointed to a source far beyond our galaxy. But back then, nothing in known astrophysics could explain such a short, energetic pulse from so far away. Some researchers even wondered if it was secret military radar bouncing off the moon. It took the discovery of more FRBs to vindicate Lorimer's find, proving the universe was full of these cryptic flashes. What's often overlooked is how this single burst rewrote the rules. Before 2007, nobody was actively looking for millisecond radio pulses from deep space. The Lorimer burst forced astronomers to ask, what could possibly generate this much energy this fast? The answer still eludes us, but the question launched an entire field of study. Today's FRB hunters owe their careers to that one anomaly, a reminder that sometimes the biggest discoveries aren't made by those seeking them, but by those willing to take a second look at what everyone else ignored. The burst's legacy isn't just scientific, it's philosophical. It taught us that the cosmos operates on scales we're only beginning to fathom. 5 milliseconds of radio waves unnoticed for years became the key to unlocking one of space's greatest modern mysteries. And that's the beauty of astronomy. Sometimes the universe hides its most profound lessons in the tiniest bursts of static. In the summer of 2020, astronomers caught something extraordinary, a tantalizing whisper from our cosmic backyard. A narrowband radio signal, dubbed BLC1, appeared to originate from Proxima Centauri, the closest star system to our Sun and home to at least one potentially habitable planet. For a brief moment, it seemed like humanity might have stumbled upon the holy grail of space exploration. Evidence we're not alone. The signal was detected by the Breakthrough Listen project, which scans nearby stars for signs of intelligent life, and it ticked all the right boxes: unusual frequency structure, no obvious natural explanation, and an origin point that set imaginations racing. What made BLC1 so electrifying was its specificity. Unlike the chaotic bursts of natural cosmic phenomena, this signal occupied a tight band of radio frequencies, the kind typically cluttered with human-made interference. But here's the twist: it drifted in frequency over time, just as you'd expect from a distant transmitter on a moving planet. Researchers ruled out satellites, aircraft, and ground-based sources, and for a fleeting moment, the possibility of contact felt real. Social media erupted with speculation. Headlines blared about alien messages, and even seasoned scientists allowed themselves cautious optimism. But the universe loves a good plot twist. As the data underwent rigorous scrutiny, cracks began to show. The signal's frequency drift, initially seen as a hallmark of extraterrestrial origin, turned out to match the behavior of oscillators in everyday electronics. Then came the clincher. Further analysis revealed nearly identical signals popping up at other frequencies, a telltale sign of human-made interference. The final nail in the coffin: BLC1 only appeared when the telescope was pointed at Proxima Centauri, but vanished when aimed slightly away, suggesting the signal wasn't cosmic at all, but a rogue radio wave bouncing around our own atmosphere or equipment. Yet BLC1's story isn't just a cautionary tale about false alarms. It exposed a fascinating challenge in the search for extraterrestrial intelligence. Our own planet is noisy. Between cell phones, satellites, and microwave ovens, Earth leaks radio waves like a sieve, creating a minefield of false positives. But the episode also proved something profound: our detection methods are sharpening. The fact that scientists could pinpoint BLC1's likely origin with such precision shows how far the field has come since the days of the WOW signal. So was BLC1 a letdown? Only if you ignore what it taught us. It forced researchers to refine their filters to better distinguish cosmic whispers from terrestrial chatter. And in doing so, it brought us one step closer to the day when, if the universe is feeling generous, we might finally intercept a signal that changes everything. Until then, every false alarm is a dress rehearsal, a reminder that the greatest discoveries often begin with a tantalizing maybe. Some stars flicker gently as planets pass in front of them, but KIC 8462852, better known as Tabby's star, doesn't play by those rules. This bizarre celestial object, discovered by citizen scientists in the Kepler mission data, behaves like no other. Instead of predictable, slight dimming from orbiting worlds, its light curves plunge erratically, sometimes by a staggering 22%. Imagine if our sun suddenly lost a fifth of its brightness for days or weeks, then snapped back to normal without explanation. That's the kind of cosmic tantrum this star throws, leaving astronomers utterly bewildered. The mystery deepened when researchers combed through historical records and found something even stranger. The star appeared to be gradually fading over decades, as if something colossal was slowly blocking its light. Enter the most sensational explanation, the alien megastructure hypothesis. The idea was that an advanced civilization might be building a Dyson swarm, a vast array of energy-collecting panels encircling the star, causing those irregular dips. Suddenly, Tabby's star wasn't just an oddity. It was a potential billboard for extraterrestrial engineering, capturing imaginations worldwide. But science thrives on skepticism, and alternative theories soon emerged. One leading explanation points to massive clouds of dust, possibly from disintegrating comets or colliding planets. Unlike solid megastructures, dust behaves unpredictably, clumping, dissipating, and scattering light in ways that match the star's strange dimming patterns. Another theory suggests a family of giant, irregularly shaped debris rings, like Saturn's, but on a scale so vast they dwarf our entire solar system. These natural explanations gained traction when follow-up observations revealed the dimming was more pronounced in blue light than red, a telltale sign of dust scattering, not opaque alien construction. What makes Tabby's star so compelling isn't just the wild theories it spawned, but how it reshaped astronomy itself. Before its discovery, nobody thought to look for stars behaving this way. Now, an entire field of stellar oddballs has emerged, with researchers combing through telescope data for similar anomalies. The star also showcased the power of citizen science. It was volunteers, not professional astronomers, who first flagged its weirdness in Kepler's data, proving that cosmic breakthroughs can come from anywhere. The latest twist: even after years of scrutiny, Tabby's star refuses to give up all its secrets. While dust remains the favored explanation, some dips still defy easy categorization, leaving room for lingering questions. Could there still be a hint of something extraordinary hidden in the noise? Or is the truth simply a reminder that nature, in its infinite creativity, will always outpace our imagination? One thing's certain: this star taught us that the universe is weirder, messier, and more wonderful than we ever dreamed, and that sometimes the most thrilling mysteries aren't about finding answers, but about learning just how much we have left to discover. Amid the cosmic noise of deep space, one signal has stubbornly refused to fade into obscurity: SHGb02+14a. Discovered in 2003 by SETI Home Computing Project, this faint radio whisper emerged from the constellation Pisces, pulsing with a frequency that immediately raised eyebrows: 1,420 MHz, the same as the famous WOW signal. Unlike a cosmic one-hit wonder, this one kept coming back, detected not once but multiple times over several years, always drifting slightly in frequency as though its source were moving. At first glance, SHGb02+14a seemed to check all the boxes for an artificial signal: narrowband, drifting, and persistent. But here's where things get murky. The signal was incredibly weak, barely rising above the background static, and its origin point didn't align with any known star system within 1,000 light-years. Even stranger, its drift rate suggested a transmitter moving at nearly 3 times Earth's orbital speed, an unusual velocity for a planet, let alone a spacecraft. Skeptics were quick to point out that atmospheric interference or even a glitch in the home computers processing the data could explain the anomaly, yet the signal's persistence kept it alive in scientific debates. Could it be a fluke? Absolutely. But flukes don't usually repeat in the same patch of sky with such peculiar consistency. Some researchers floated the idea of a naturally occurring maser, a cosmic amplifier created by molecules in space, yet none matched SHGb02+14a's exact profile. Then there's the fringe possibility. What if it was artificial but not in the way we imagine? A malfunctioning alien probe, perhaps, or a beacon whose true purpose we simply don't comprehend. What makes this signal so fascinating isn't its credibility. Most scientists rank it low on the likely alien scale. But what it reveals about the challenges of hunting for extraterrestrial intelligence. In a universe awash with natural radio emissions, picking out a potential hello is like listening for a whisper in a hurricane. SHGb02+14a, for all its ambiguity, became a test case for refining detection methods, teaching researchers to filter out earthly interference and cosmic static with greater precision. Years later, the signal remains unexplained, a quiet enigma buried in the archives. It may never graduate from curiosity to breakthrough, but that's the nature of cosmic detective work. Not every clue leads to an answer. Sometimes the most valuable mysteries are the ones that remind us how little we truly know, and how much wonder still hides in the static between the stars. In 2015, a signal from a star 195 light-years away sent shockwaves through the astronomy community, then vanished into controversy almost as quickly as it appeared. Detected by the Ratan 600 radio telescope in Russia, this burst of radio waves came from HD 164595, a star eerily similar to our own Sun, complete with at least one known Neptune-like planet orbiting it. The signal was narrowband, centered around 11 GHz, a frequency with little natural background noise, making it a prime candidate for artificial transmission. For a brief, electrifying moment, headlines blared about potential alien contact, and scientists scrambled to verify what could have been humanity's first encounter with an intelligent civilization beyond Earth. The excitement wasn't entirely unfounded. HD 164595's sun-like nature raised tantalizing possibilities. If life could emerge here, why not there? The signal's intensity also sparked speculation. If it was artificial, the energy required to beam it across interstellar space would imply a civilization far more advanced than our own, capable of harnessing the power of an entire star. But the euphoria was short-lived. Within days, alternative explanations emerged. The signal's frequency overlapped with known military and satellite bands, and skeptics pointed out that its detection hadn't been independently confirmed by other telescopes, a critical step in ruling out earthly interference. Then came the knockout punch. Further analysis revealed the signal's origin wasn't fixed in the sky, but moved in a way that matched geostationary satellites, human-made objects orbiting Earth. The final nail in the coffin. The signal never reappeared in follow-up observations, a hallmark of terrestrial interference rather than a persistent cosmic source. What initially seemed like a message from the stars turned out to be little more than a cosmic mirage, a trick of radio waves bouncing through our own technological backyard. Yet the story of HD 164595 isn't just about a false alarm. It's a masterclass in the delicate dance of scientific skepticism and optimism. The signal's brief moment in the spotlight exposed a harsh reality. Our planet is drowning in radio noise from cell towers to radar systems, making it incredibly difficult to isolate true cosmic signals. But it also highlighted how far we've come. Unlike the WOW signal era, modern astronomers now have protocols, rapid response teams, cross-verification with other observatories, and advanced filtering techniques to quickly separate potential breakthroughs from terrestrial static. So was HD 164595 a disappointment? Only if you ignore the lessons it taught us. It proved that the search for extraterrestrial intelligence isn't just about listening. It's about learning to distinguish the universe's whispers from our own electronic chatter. And perhaps that's the most valuable signal of all, a reminder that every dead end brings us one step closer to tuning into the right frequency. In 2016, the Ratan 600 radio telescope in Russia picked up a signal that sent astronomers and alien hunters into a frenzy, a pulse of radio waves seemingly emanating from the direction of HD 164595, a sun-like star just 94 light-years away. The discovery first surfaced in a leaked report, and before scientists could properly analyze the data, headlines exploded with claims of a potential alien transmission. What made this particular signal so intriguing was the star itself, a near twin of our Sun, already known to host at least one Neptune-sized exoplanet. The implication was irresistible. If life could arise around a star like ours, why not here? The signal's technical details only fueled speculation. It appeared to be narrowband, the kind of focused transmission often associated with artificial sources, and centered around 11 GHz, a frequency notably quiet in nature, making it a prime candidate for intentional broadcasting. Media outlets ran wild with scenarios. Was this a deliberate beacon, an accidental leak from an advanced civilization, or even the remnants of some long-dead society's technology? The excitement reached such a pitch that even SETI scientists diverted telescopes to monitor the star, hoping to catch a repeat of the signal. But the scientific process thrives on skepticism, and cracks soon appeared in the extraterrestrial hypothesis. Independent teams failed to detect any repeat signals, a red flag in radio astronomy where natural phenomena, or even alien messages, tend to recur. Then came the damning evidence. Further analysis revealed the signal's characteristics matched those of Earth-orbiting satellites. The telltale clue: its apparent motion across the sky aligned perfectly with the trajectories of human-made spacecraft, not a distant star. The coup de grace was delivered when researchers realized the signal's frequency overlapped with bands commonly used by military and communication satellites, effectively ruling out a cosmic origin. Yet the story of HD 164595's phantom signal isn't just a cautionary tale about media hype. It underscores a critical challenge in the search for extraterrestrial intelligence. Our planet is a cacophony of radio noise, and distinguishing a true cosmic signal from terrestrial interference is like isolating a single voice in a roaring stadium. The episode also highlighted the delicate dance between scientific transparency and sensationalism. The initial leak, likely intended to prompt peer scrutiny, instead sparked a wildfire of speculation, a reminder that in the age of viral headlines, even tentative data can take on a life of its own. What's often overlooked is how this near miss advanced the field. The rapid response from astronomers worldwide demonstrated the growing coordination among SETI researchers, who now have protocols to quickly verify or debunk potential signals. Tools like the Breakthrough Listen initiative have since refined their methods, employing machine learning to filter out human-made interference with unprecedented precision. In a way, the Ratan 600 signal was a dress rehearsal, preparing scientists for the day when, if the universe wills it, a genuine alien transmission might finally crackle across our telescopes. So while HD 164595's brief moment in the spotlight ended not with a revelation but a shrug, its legacy lingers. It taught us that the line between discovery and false alarm is razor thin, and that patience is as vital as technology in deciphering the universe's whispers. And perhaps that's the most valuable lesson of all. In the grand search for cosmic company, every dead end still brings us closer to tuning our ears and our instruments to the right frequency. Canada's CHIME telescope isn't just another eye on the sky. It's a revolutionary machine built to catch the universe's most elusive whispers. Perched in the mountains of British Columbia, this sprawling array of half-cylinders looks more like a futuristic skate park than a scientific instrument, but don't let its unconventional design fool you. CHIME's real superpower is its ability to scan the entire northern sky every single day, making it the ultimate detective for fleeting cosmic signals. And in 2018, it struck gold with a discovery that rewrote the rulebook on fast radio bursts. FRB 180916, the first FRB ever caught in a predictable, repeating rhythm. What set this burst apart wasn't just its repetition, it was its uncanny 16-day cycle. Like clockwork, the signal would fire off bursts for 4 days, then fall silent for 12, over and over again. This wasn't random chaos, it was a cosmic heartbeat, hinting at an underlying mechanism far more structured than anything astronomers had dared to predict. The implications were staggering. If FRBs could follow schedules, their sources couldn't be cataclysmic one-offs like colliding stars. Instead, they pointed to objects that endure, magnetars wobbling on unstable axes, perhaps, or binary systems where a neutron star's orbit periodically funnels energy into focused beams. Chime didn't stop there. As it kept listening, it uncovered dozens more repeating FRBs, each with its own unique fingerprint. Some spat out bursts in erratic clusters like a cosmic machine gun, while others pulsed with near mathematical precision. Yet FRB 180916 remained the crown jewel, not just for its regularity, but for something even more tantalizing. When scientists traced its origin, they found it came from the outskirts of a spiral galaxy 500 million light-years away, nestled in a region humming with star formation. That location was a vital clue. Magnetars, the leading suspects for FRBs, are born from the explosive deaths of massive stars, exactly the kind forged in these stellar nurseries. But here's where the mystery deepens. If magnetars are the culprits, why don't all FRBs repeat? Why do some fire once and vanish, while others, like 180916, adhere to strict schedules? One theory suggests it's all about environment. A magnetar trapped in a dense debris field might produce one-off bursts as it plows through clumps of material, while one orbiting another star could get tidally yanked into periodic eruptions. Another idea throws black holes into the mix. Imagine a neutron star dancing around a black hole, its bursts triggered each time it swings through a disk of superheated gas. Chime treasure trove of repeating FRBs has done more than just fill textbooks. It's forced us to rethink how energy operates on cosmic scales. These aren't just flashes in the dark, they're probes into the most extreme physics imaginable, from the warped spacetime around neutron stars to the magnetic storms that could shred atoms. And with every new detection, Chime pulls back another layer of the curtain, proving that even in the vast, chaotic universe, patterns emerge, if only we have the patience and the right tools to listen for them. The Parkes Radio Telescope in Australia has earned its place as a cosmic eavesdropper, uncovering some of the universe's most baffling signals. But not all of them turned out to be extraterrestrial. Among its most infamous discoveries were the so-called peritons, bursts of radio waves that initially fooled scientists into thinking they'd stumbled upon a new astrophysical phenomenon. These signals had all the hallmarks of something cosmic, brief, intense, and seemingly random, yet they carried a peculiar quirk. They only appeared during working hours at the observatory. That odd timing was the first clue that something far more mundane might be at play. For years, astronomers scratched their heads over these bursts, which seemed to come from all directions in the sky. The mystery deepened when researchers noticed the signals were strongest when the telescope was pointed toward the horizon, unlike genuine cosmic signals, which remain consistent regardless of orientation. Then came the breakthrough. A sharp-eyed technician realized the periton's frequency matched the microwave emission band used by household microwave ovens. The final piece fell into place when someone at the observatory cafeteria opened a microwave door mid-cycle, and like magic, the telescope picked up an identical burst. The culprit, leaking radiation from a microwave oven interrupting its own timer, creating a radio burp that the sensitive telescope mistook for a cosmic event. But the peritons weren't just a comical mix-up, they became a masterclass in scientific humility. Their eventual explanation exposed a critical blind spot in signal detection, the assumption that anything picked up by a radio telescope must originate in space. In reality, Earth's own technological clutter, microwaves, cell phones, even passing airplanes can masquerade as cosmic phenomena. This revelation forced astronomers to tighten their protocols, implementing stricter filters to weed out terrestrial interference before attributing signals to the cosmos. The story doesn't end there, though. Parkes has also been the source of legitimate breakthroughs, like its role in detecting fast radio bursts. The same telescope that once mistook kitchen appliances for cosmic whispers later confirmed the existence of FRBs as genuine astrophysical events. This duality, false alarms alongside real discoveries, highlights a fundamental truth about exploring the unknown. Progress often comes hand in hand with missteps. Every time a signal turns out to be a microwave oven or a satellite, it sharpens the tools scientists use to recognize the real McCoy. What makes the Parkes signals so fascinating isn't just the mix of cosmic and kitchen sink explanations, it's how they expose the delicate dance between skepticism and wonder in astronomy. For every legitimate mystery like FRBs, there are a dozen Puritans waiting to lead researchers down the wrong path. Yet each dead end teaches something new, whether it's refining detection methods or learning to question even the most tantalizing data. In the end, the most valuable signal Parkes ever picked up might not have been from the stars at all, but from a humble microwave reminding us that the universe's greatest lessons often come in the most unexpected forms. In 1967, a graduate student named Jocelyn Bell Burnell was meticulously reviewing data from a newly built radio telescope when she stumbled upon something extraordinary. A series of rapid, perfectly timed pulses arriving every 1.337 seconds. The signal was so precise, so unnaturally regular, that for a brief, electrifying moment, her team jokingly labeled it LGM1, short for Little Green Men. It wasn't just the rhythm that felt artificial. The pulses came from a fixed point in space, unlike the chaotic bursts typical of cosmic noise. The possibility that they might be detecting an alien beacon was impossible to ignore. What made this discovery so jarring was its defiance of expectations. At the time, astronomers assumed any signals from deep space would be either random or slow, like the lazy undulations of radio galaxies. But this was a cosmic metronome, ticking with clockwork precision across 240 megahertz of bandwidth. The team kept the finding secret for months, quietly ruling out every earthly explanation: satellites, radar echoes, even malfunctioning equipment. But the signal persisted, clear as a bell, and soon others like it were found elsewhere in the sky. The truth, when it finally emerged, was almost as astonishing as the prospect of alien contact. These weren't messages from extraterrestrials, but something just as mind-bending: rapidly spinning neutron stars, the dense corpses of massive stars that had gone supernova. As these stellar remnants rotated, their powerful magnetic fields funneled beams of radiation into space like cosmic lighthouses, sweeping past Earth with each spin to create those rhythmic pulses. The discovery earned Bell Burnell's advisor a Nobel Prize, though controversially. She was excluded and birthed an entirely new field of astrophysics. Yet the legacy of LGM1 runs deeper than just scientific accolades. It forced astronomers to confront their assumptions about what constitutes natural in the cosmos. Before pulsars, nobody imagined celestial objects could behave with such machine-like regularity. Their existence revealed the universe's capacity for precision engineering on a scale humans could barely fathom. Neutron stars packing more mass than the Sun into a city-sized sphere, spinning hundreds of times per second without flying apart. Pulsars also became celestial tools, their clockwork ticks allowing scientists to test Einstein's theories with unprecedented accuracy. When the first binary pulsar was discovered, its orbital decay matched general relativity's predictions perfectly, providing indirect evidence for gravitational waves decades before LIGO detected them directly. Others served as cosmic GPS beacons, helping map the Milky Way's magnetic fields. But perhaps the most poetic twist is how pulsars blurred the line between the natural and the artificial. Their signals, so easily mistaken for alien broadcasts, ended up revealing a universe far stranger than fiction, one where the corpses of dead stars spin, hum, and shine like interstellar lighthouses. Every time an astronomer detects a new pulsar, it's a reminder of that exhilarating moment in '67 when we first glimpsed the cosmos's hidden rhythms and realized that sometimes the truth is just as wondrous as the fantasy. Rising from the heart of the Milky Way like two colossal, ghostly balloons, the Fermi bubbles stretch 50,000 light-years across half the width of our entire galaxy. Discovered in 2010 by NASA's Fermi Gamma-Ray Space Telescope, these gargantuan structures glow with high-energy gamma rays, towering above and below the galactic plane in near-perfect symmetry. Imagine standing on Earth and looking toward the night sky, only to realize you're staring at the base of an invisible monument so vast, its edges would take light 25,000 years to traverse. And the strangest part, no one knows exactly how they got there. For all their breathtaking scale, the Fermi bubbles are surprisingly subtle. They don't emit visible light, just a faint haze of gamma rays detectable only by specialized instruments. But their energy tells a violent story. The particles within these bubbles are moving at nearly the speed of light, suggesting a cataclysmic event in our galaxy's past. One leading theory points to Sagittarius, a star, the supermassive black hole at the Milky Way center. Astronomers speculate that millions of years ago, this cosmic monster might have gone through a feeding frenzy, devouring enormous amounts of gas and dust. As material spiraled into the black hole's maw, it could have launched twin jets of energized particles straight up and out of the galaxy's disk, like a cosmic fire hose blasting into the void, leaving behind these lingering radioactive echoes. But there's a twist. Not all scientists are convinced by the black hole jet explanation. Some argue the bubbles could be remnants of a starburst period, when a flurry of supernova in the galactic center collectively unleashed enough energy to blow these gigantic cavities into space. Others propose even wilder ideas, like dark matter particles annihilating one another in vast, invisible clouds. The debate rages because, unlike most cosmic phenomena, the Fermi bubbles don't come with an instruction manual. They're a fossil record of something monumental. We just can't agree on what. What makes these structures especially fascinating is their age. Based on their current size and expansion rate, astronomers estimate they're somewhere between 2 and 4 million years old, relatively young in cosmic terms. That means if we'd had gamma-ray eyes a few million years ago, we might have witnessed their birth in real time. Picture it, early hominids walking the Earth, blissfully unaware that their galaxy's heart was erupting in a burst of energy powerful enough to sculpt bubbles larger than anything humans could conceive. The Fermi bubbles aren't just a scientific curiosity, they're a reminder that even our own galaxy harbors secrets we're only beginning to uncover. They challenge our assumptions about how galaxies evolve, how black holes behave, and what happens when the universe decides to leave its mark on the cosmos. And as telescopes grow more advanced, these enigmatic structures might finally give up their secrets, revealing not just how they came to be, but what they can teach us about the turbulent, dynamic galaxy we call home. The solar system has hosted countless visitors over billions of years, but none have sparked as much intrigue or outright controversy as the mysterious traveler known as Oumuamua. When this interstellar object was first spotted in October 2017, it was already speeding away from Earth at nearly 200,000 miles per hour, making its brief appearance a mad dash for scientists to gather data. At first glance, it seemed like just another asteroid until the anomalies started piling up. For starters, its shape defied all expectations. Most space rocks resemble lumpy potatoes, but Oumuamua was elongated, stretching perhaps 600 feet in length while being just a tenth as wide, like a cosmic cigar tumbling through the void. Then came the real shocker. As it hurtled past the sun, it didn't just follow the predictable path of gravity. Instead, it accelerated slightly, as if something were giving it an extra push. That tiny but undeniable nudge sent astronomers into a frenzy of speculation. Comets often speed up thanks to evaporating ice, but Oumuamua showed no visible tail or gas cloud. So what was propelling it? One radical theory came from Harvard astrophysicist Avi Loeb, who suggested the object might be artificial, a discarded light sail from an alien civilization, using radiation pressure to navigate the stars. The idea made headlines worldwide, but most scientists weren't convinced. Alternative explanations ranged from the exotic to the downright bizarre. Some proposed it was a chunk of frozen hydrogen, a hydrogen iceberg, vaporizing invisibly as it warmed near the sun, explaining both the acceleration and lack of a tail. Others speculated it could be a fractal-like dust aggregate, so porous it behaved more like a cosmic sponge than a solid rock. The debate raged because Oumuamua refused to fit neatly into any known category. It wasn't quite a comet, wasn't quite an asteroid, and certainly didn't match any human-made object. By the time telescopes could turn toward it for detailed observations, the visitor was already too distant, leaving researchers with tantalizing fragments of data and a universe of unanswered questions. Was it a freak of nature or something more? What makes Oumuamua so compelling isn't just its strange properties, it's the door it kicked open in astronomy. Before 2017, no one had ever confirmed an interstellar object passing through our solar system. Now we know they're out there, and future discoveries might finally help us piece together what this enigmatic traveler truly was. Until then, Oumuamua remains a cosmic riddle, a fleeting guest that challenged our assumptions and left us wondering just how many more surprises are drifting between the stars. The universe isn't just expanding, it's doing so unevenly, as if some invisible hand is tugging entire galaxy clusters toward a point beyond the cosmic horizon. Astronomers call this enigma dark flow, and it's one of the most baffling discoveries in modern cosmology. Imagine throwing leaves into a river, only to watch them all drift stubbornly in one direction against the current. That's essentially what's happening with hundreds of galaxy clusters, all streaming toward a mysterious gravitational anomaly at speeds exceeding 2 million miles per hour, a phenomenon that shouldn't exist according to our standard model of the universe. When NASA Wilkinson Microwave Anisotropy Probe first detected this motion in 2008, it sent shockwaves through the scientific community. These weren't just random celestial movements. The clusters were aligning along a vector pointing toward the constellations Centaurus and Hydra, as if drawn by something colossal lurking in uncharted space. The strangest part, there's no known mass, no supercluster, no cosmic void that could generate such a vast gravitational pull. Even dark matter, the universe's invisible scaffolding, can't explain it. Some researchers estimate the source would need to be hundreds of billions of light-years away, far beyond the observable universe's edge. This revelation sparked radical theories, the most mind-bending being that dark flow might be evidence of a neighboring universe. In certain multiverse models, other universes could exist as bubbles in an infinite cosmic foam, each with its own physical laws. If one of these bubbles brushed against ours during the Big Bang, it might have left behind a gravitational imprint, a cosmic wake dragging galaxies toward it like iron filings to a magnet. It's an idea straight out of science fiction, yet for now, it remains one of the few explanations that doesn't collapse under scrutiny. Skeptics argue the dark flow could be an illusion caused by uneven cosmic expansion or incomplete data, but follow-up studies with the Planck satellite only deepen the mystery. While Planck measured a weaker flow than WMAP, it still confirmed the trend, ruling out instrumentation errors. The disagreement between the two datasets has led to heated debates, with some scientists proposing the flow might be a remnant of the universe's violent infancy, a relic from when space-time itself was still rippling from the Big Bang's aftermath. What makes dark flow so revolutionary isn't just its defiance of cosmology's rulebook, it's the philosophical implications. If proven real, it suggests our universe isn't the isolated, self-contained system we've long assumed, but part of something vastly larger and stranger. Every new observation peels back another layer, revealing how much we still don't understand about the fabric of reality. Whether it's a window into the multiverse or a flaw in our cosmic math, one thing is certain. The universe is moving in ways we never expected, and the truth might be more extraordinary than we dare imagine. Hidden in the faint glow of the cosmic microwave background, the afterimage of the Big Bang itself lies an anomaly so peculiar it's been called the universe's first bruise. Stretching nearly 2 billion light-years across, the CMB cold spot is a vast region of space where temperatures are mysteriously lower than the surrounding cosmos by about 70 microkelvin. At first glance, that might not sound like much, but in the ultra-precise world of cosmology, it's as glaring as a frozen lake in the middle of a desert. When scientists first spotted this frigid patch in data from NASA's Wilkinson Microwave Anisotropy probe, they assumed it was a fluke, a trick of statistical noise. But as more advanced telescopes like Planck confirmed its existence, the plot thickened. The cold spot isn't just a little cooler, it defies the standard model of cosmology's predictions with odds of less than 1 in 50. So what could possibly leave a cosmic chill of this magnitude? One leading theory points to a supervoid, a mind-bogglingly empty region of space where galaxies are eerily scarce. In such a void, photons from the CMB would lose energy as they traverse the expanding space, creating a colder spot in the microwave sky. But here's the catch. When astronomers scanned the cold spot's location with optical telescopes, they found no void large enough to explain the temperature drop. The ones they did discover were puny by comparison, leaving a glaring gap between prediction and observation. That's where things get really wild. Some researchers suggest the cold spot might be evidence of a collision with another universe, a multiverse theory made tangible. Imagine our universe brushing against a neighboring bubble during its infancy, leaving behind a gravitational imprint like a fingerprint on glass. The idea sounds like science fiction, but it's grounded in legitimate physics. Quantum fluctuations during cosmic inflation could have spawned countless universes, and if one bumped into ours, the energy transfer might have created this anomalous cold patch. Yet even this exotic explanation has its skeptics. Alternative proposals range from cosmic textures, exotic defects in spacetime's fabric, to primordial black holes distorting light from the early universe. The cold spot's persistence in the data keeps these debates alive, a reminder that the universe's oldest light still holds secrets we've barely begun to decode. What makes this icy enigma so compelling isn't just its defiance of explanation, but what it reveals about the limits of our cosmic maps. The CMB is supposed to be the universe's baby picture, a nearly uniform snapshot of its fiery birth. But the cold spot whispers that the story might be more complex, that wrinkles in the cosmic blanket could hint at forces beyond our current understanding. Whether it's a void we can't see, a collision we can't fathom, or something entirely new, one thing's certain: the universe's coldest mystery might just hold the key to its warmest revelations. Among the countless stars dotting our galaxy, a handful stand out not for their brilliance, but for their bizarre infrared signatures glowing far more than they should. These oddballs, known as Dyson sphere candidates, have set astronomers' pulses racing with the tantalizing possibility that we might be glimpsing the handiwork of an advanced civilization. The idea traces back to physicist Freeman Dyson, who speculated in 1960 that an alien society harnessing all its stars' energy might build vast solar collectors encircling it, leaking telltale heat detectable across interstellar space. Take TOC 6111-1162-1, a star roughly 1,200 light-years away that made headlines in 2016. Observations from NASA's WISE telescope revealed its infrared glow was wildly lopsided, like a lumpy, half-finished shell warming unevenly around its host star. The pattern didn't match typical dust disks or young stellar nurseries, sparking speculation about artificial origins. Could this be a partially constructed Dyson swarm, a civilization in the slow process of encasing its sun? But cosmic mysteries rarely surrender to simple answers. Natural explanations quickly emerged. One study suggested the star might be slurping up a nearby planet or moon, its gravity shredding the unfortunate world into a spiraling debris field that glows with absorbed starlight. Others pointed to interstellar dust clouds drifting between us and the star, filtering its light in unexpected ways. The most compelling counterargument came from follow-up observations showing similar stars with matching infrared quirks, statistically unlikely if each anomaly represented alien engineering. What makes these candidates so fascinating isn't just their potential for extraterrestrial contact, but how they force us to rethink the boundary between nature and technology. The universe is full of astrophysical phenomena that mimic artificial constructs. Pulsars were once mistaken for alien beacons, after all. Yet the search persists because the stakes are cosmic, confirming even one Dyson structure would rewrite humanity's place in the universe, proving we're not the only builders among the stars. Current efforts now focus on distinguishing truly exotic signatures from cosmic false alarms. Projects like the Galileo Initiative are developing methods to separate mundane dust rings from potential megastructures, while machine learning scans vast star catalogs for hidden patterns. The hunt has even expanded beyond infrared. Some researchers now listen for laser pulses or radio silence from candidate systems, theorizing an advanced civilization might shift to more efficient communication as it grows. Whether these odd stars are alien power plants or celestial oddities, their legacy is secure. They've expanded how we imagine life's cosmic footprint. After all, if a civilization did reshape its star, the evidence might not be a flashing beacon, but something far subtler, a whisper of wasted heat, a shadow across starlight, waiting centuries for someone to notice. Deep in the crowded starfields of the Milky Way, a sun named VVVWIT-07 pulled off one of the most dramatic vanishing acts ever recorded, fading by a staggering 80% before brightening again months later, as if a cosmic hand had flicked a dimmer switch. This wasn't the slow, uneven dimming of Tabby's star, but something far more abrupt, like a celestial curtain dropping across its face. Discovered in 2021 by the Vista telescope in Chile, the star's bizarre behavior immediately drew comparisons to its more famous cousin, but with a twist. Where Tabby's star teased with unpredictable dips, VVVWIT-07 light curve resembled a perfect symmetrical V, a textbook signature of something solid passing squarely in front of it. The leading theory, a colossal, opaque disk, possibly debris from a shattered planet or a protoplanetary remnant orbiting an invisible companion star. Picture a Jupiter-sized hoop of dust and rock, tilted just right to eclipse the primary star from our vantage point every few decades. Such occultation events aren't unheard of in astronomy, but the scale here is mind-bending. For the star to dim so severely, the eclipsing object would need to stretch hundreds of times wider than its host star, far larger than any known planet or conventional debris field. This suggests we're witnessing something extraordinarily rare, either a transient cosmic accident or a previously unobserved class of astronomical object. Skeptics of the alien megastructure hypothesis point out the star's infrared glow holds clues. Unlike Tabby's star, where dust remains the prime suspect, VVVWIT-07 dimming showed no telltale wavelength-dependent scattering, hinting the obscuring object isn't just diffused dust, but something denser and more structured. Yet even here, nature offers plausible explanations. Binary systems with misaligned disks, like the famous Epsilon Aurigae, produce similar eclipses when their edge on debris rings glide past their stars. The key difference: VVVWIT-07 occulting disk would need to be exceptionally wide and dark, pushing the boundaries of known physics but not quite breaking them. What makes this star such a compelling puzzle isn't just its behavior, it's the timing. Unlike Tabby's star, which dims erratically, VVVWIT-07 event unfolded with almost mathematical precision, suggesting a predictable orbit. If future observations catch it dimming again on schedule, it could confirm the presence of a cosmic carousel, a slow-spinning disk larger than some solar systems, silently wheeling through space. Until then, the star remains a tantalizing reminder that the universe doesn't need aliens to build megastructures. Sometimes, gravity and chaos collaborate on creations strange enough to defy our wildest imaginations. Most galaxies are content to follow the cosmic rulebook, spiraling gracefully or hovering as featureless blobs, but a rare few break the mold with an unmistakable flair for the dramatic. Enter the X-shaped radio galaxies, celestial rebels whose colossal jets of charged particles don't just shoot outward in straight lines. They fan out into enormous, symmetrical wings, stretching hundreds of thousands of light-years to form a perfect cosmic X. These aren't just pretty patterns, they're violent fingerprints left behind by some of the universe's most cataclysmic events, and their very existence challenges everything we thought we knew about how galaxies evolve. At the heart of every X-shaped galaxy lurks a supermassive black hole, guzzling down gas and dust while spewing twin jets of plasma at nearly light speed. Normally, these jets flow steadily in opposite directions, creating classic radio lobes. But in these peculiar systems, something interrupts the flow, something powerful enough to wrench those jets sideways, sculpting them into a sprawling X. The leading suspect, a black hole merger. Picture two gravitational monsters spiraling toward each other, their colossal dance tilting the axis of the surviving black hole's spin mid-meal. As its jets suddenly find themselves pointing in a new direction, the old jets linger like fading echoes while fresh ones blast out along the updated trajectory. The result, a celestial X, marks the spot, a cosmic graffiti tag left behind by one of the universe's most violent handoffs. But mergers aren't the only explanation. Some theorists argue these shapes could emerge from backflow, jets plowing into intergalactic gas until they rebound like water hitting a wall, curling backward to form secondary lobes. Others propose the X might be an illusion, a trick of perspective where two separate galaxies align perfectly from our viewpoint. The truth is, every new X-shaped galaxy discovered seems to add another wrinkle to the mystery. Take NGC 326, one of the most studied examples, whose jets twist and kink in ways no simulation can fully replicate. Or PKS 2014-55, whose lobes glow with oddly mismatched energies, as if the galaxy can't decide which pair of wings to prioritize. What makes these galactic oddballs so fascinating isn't just their bizarre anatomy, it's what they reveal about the chaotic lives of black holes. Normally, we think of these gravitational titans as steady, predictable engines, but X-shaped galaxies expose their messy side. They show us black holes lurching, stumbling, and reshuffling their jets like cosmic DJs spinning records in the dark. Every X is a frozen moment in this turbulence, a snapshot of a system caught mid-transformation. And then there's the practical magic. These galaxies serve as natural particle accelerators, their twisted jets bending magnetic fields to hurl electrons to energies impossible to achieve on Earth. Some even glow in high-energy gamma rays, turning entire lobes into billboards for the universe's most extreme physics. For astronomers, each new X-shaped galaxy is like stumbling upon a celestial laboratory, one where the laws of plasma physics and gravity play out on scales we could never hope to simulate. Yet for all their scientific value, perhaps the greatest gift of these galaxies is the sheer audacity they represent. In a universe that often feels bound by rules, they're the rebels, the ones that prove even the mightiest black holes can still surprise us. Every X in the sky is a reminder that out there, beyond the edge of our understanding, the cosmos is still scribbling outside the lines. The cosmos glows in more ways than our eyes can see, especially in the infrared spectrum, where mysterious bands of light paint the galaxy in ghostly hues. These aren't the clean, sharp lines of atomic transitions, but broad, smudged emissions that stretch across wavelengths, appearing almost everywhere astronomers look. Dubbed the Unidentified Infrared Emission Bands, or UI, these signals have been spotted in nebulas, star-forming regions, and even the dust between stars, as if the universe dipped its brush in invisible ink and scribbled across the sky. What makes them so baffling isn't just their ubiquity, it's the fact that after decades of study, no single explanation fully accounts for their origin. The leading suspects in this cosmic whodunit are complex organic molecules known as polycyclic aromatic hydrocarbons, or PAR. Picture microscopic flakes of carbon, their atoms arranged in hexagonal rings like chicken wire, vibrating as they absorb starlight and re-emit it in the infrared. These hardy molecules are thought to form in the sooty winds of dying stars, surviving the harshness of space to drift through galaxies. When telescopes like Spitzer and James Webb catch their infrared signatures, it's like finding cosmic breadcrumbs, evidence that the building blocks of life might be more widespread than we ever imagined. But here's the twist: not all UI signals fit the pH model. Some bands appear in environments too harsh for these delicate molecules to survive, like the searing vicinity of supermassive black holes. Others show up in regions where pHs shouldn't form at all, leaving scientists scrambling for alternatives. One radical theory suggests the culprit might be tiny diamonds, nanocrystals forged in the atmospheres of carbon-rich stars and blasted into space by stellar winds. Another posits that shredded fragments of graphene, the same material used in cutting-edge tech on Earth, could be scattering infrared light in unexpected ways. The plot thickens when you consider how these bands behave in different cosmic neighborhoods. In the Orion Nebula, they blaze brightly around newborn stars, suggesting a link to young, chaotic systems. Yet they've also been detected in the frigid outskirts of the Milky Way, where temperatures hover just above absolute zero. This chameleon-like adaptability hints that multiple processes might be at play, perhaps a family of related molecules, each leaving its own fingerprint in the infrared haze. What makes the UI mystery so thrilling is its connection to life's raw materials. These emissions trace the distribution of carbon, the universe's ultimate Lego block, in forms that could someday assemble into something far more complex. Every time a telescope like Webb dissects their light, it's not just solving an astrophysical puzzle, it's reading the ingredients list of the cosmos itself, one cryptic infrared band at a time. And until we crack their code, these ghostly glows will keep whispering secrets about how the universe builds, destroys, and rebuilds the very stuff of stars, and maybe even life. In 2014, a team of astronomers made a startling announcement: they might have finally detected dark matter, not through its gravitational pull, but via mysterious radio waves emanating from deep space. The signal, picked up by the European Low-Frequency Array Telescope, seemed to originate from multiple galaxy clusters, humming at a frequency that matched theoretical predictions for dark matter particles called actions. These hypothetical particles, long hunted by physicists, were thought to convert into radio waves in the presence of strong magnetic fields, and here, at last, was what appeared to be their elusive fingerprint. The discovery sent ripples through the scientific community, offering a potential breakthrough in one of cosmology's most stubborn mysteries. But as with any extraordinary claim, skepticism followed swiftly. Other researchers pointed out that the signal's frequency could also align with mundane sources, like synchrotron radiation from electrons spiraling around magnetic fields, a common phenomenon in galaxy clusters. Worse yet, when independent teams tried to replicate the findings using different telescopes, many came up empty-handed. The original researchers stood by their data, arguing that the signal's unique spatial distribution concentrated in clusters with strong magnetic fields still pointed to something unconventional. Yet without a definitive smoking gun, the debate settled into an uneasy stalemate, leaving the radio waves suspended between discovery and doubt. What makes this claim so tantalizing isn't just the possibility of cracking the dark matter enigma, it's the audacity of the method itself. For decades, scientists have chased dark matter underground in particle colliders and through painstaking astronomical surveys, all with little to show for it. The idea that dark matter might broadcast its presence via radio waves, like a cosmic radio station tuned to a frequency we'd only just discovered, was both thrilling and humbling. It forced physicists to consider that the answer might not lie in ever larger detectors or more powerful accelerators, but in the subtle whispers of the universe's oldest light. The search hasn't ended. New telescopes like the Square Kilometre Array are being designed with the sensitivity to revisit these radio anomalies with unprecedented precision. Meanwhile, theorists continue refining action models, calculating how different environments from galaxy clusters to neutron stars might coax dark matter into revealing itself. Whether the 2014 signal ultimately fades into obscurity or emerges as a landmark discovery, it's already reshaped how we hunt for the invisible 85% of the universe's matter. After all, if dark matter is truly out there, it's not just hiding, it might be singing. We just need to learn how to listen. For decades, astronomers have pondered a tantalizing possibility. What if some of the universe's mysterious signals aren't cosmic accidents, but deliberate attempts at communication? This idea, known as the alien beacon hypothesis, suggests advanced civilizations might intentionally broadcast their presence using frequencies and patterns designed to stand out against the background noise of the cosmos. One of the most compelling candidates for such a beacon lies in the so-called water hole, a quiet band of the radio spectrum nestled between the frequencies of hydrogen at 1,420 MHz and hydroxyl at 1,660 MHz. These two molecules, essential ingredients for water, make this region symbolically significant. If extraterrestrials wanted to send a message, where better to place it than in the electromagnetic equivalent of a cosmic oasis? The logic behind targeting the water hole is surprisingly elegant. Hydrogen and hydroxyl serve as the universe's natural signposts, fundamental components of interstellar chemistry that any technologically advanced species would recognize. Broadcasting here would be like setting up a meeting point in the most obvious location imaginable. SETI researchers have prioritized this frequency range for decades, scanning it with radio telescopes in hopes of catching an intentional transmission. The WOW signal, that famous 72-second burst detected in 1977, just happened to align perfectly with the hydrogen line, sparking speculation that it might have been more than a random cosmic blip. But the beacon hypothesis goes beyond just picking the right frequency. Advocates argue that truly deliberate signals would pack other telltale signs, narrowband transmissions to minimize interference, slow frequency drifts to account for relative motion between stars, or even embedded mathematical sequences to flag their artificial origins. Some propose that advanced civilizations might use lighthouse strategies, pulsing signals in predictable intervals to conserve energy while maximizing detectability. Others imagine SETI beacons positioned near gravitational lenses, where the bending of light around massive objects like stars could amplify signals across vast distances. Critics, however, point out the staggering challenges. For a beacon to be effective, it would require energy outputs dwarfing humanity's entire power grid, sustained over centuries or millennia. There's also the paradox of the ephemeral signal. If a civilization broadcasts for only a brief window in its history, the odds of another species listening at exactly the right moment are astronomically slim. And then there's the eerie silence itself. Despite decades of searching, no repeating, clearly artificial signal has ever been confirmed. Yet the search continues, fueled by advancements in technology and sheer curiosity. Modern initiatives like Breakthrough Listen deploy machine learning to sift through millions of radio channels simultaneously, filtering out earthly interference while flagging anomalies that fit beacon-like profiles. Meanwhile, alternative approaches scan for optical or infrared laser pulses, hypothetical alien internet signals traveling at the speed of light. The underlying assumption is the same. If someone out there is shouting into the void, they'd want to make it as easy as possible for us to hear them. Whether any of the universe's enigmatic signals are truly deliberate remains one of science's greatest unanswered questions. But the very act of searching reshapes how we see our place in the cosmos. Every time a telescope tunes to the waterhole or a new algorithm passes the static, we're not just hunting for aliens, we're testing a profound idea. That in a universe so vast, someone might be reaching out, not with randomness but with purpose. And if that's true, the greatest discovery in human history could be just one frequency away. The Sun, our nearest star, is anything but quiet. Flares, sunspots, and solar winds create a constant symphony of electromagnetic noise. But buried in this cosmic cacophony are radio bursts so bizarre, they defy everything we know about solar physics. These aren't your garden variety solar flares or the predictable pulses of coronal mass ejections. Instead, they're short, intense blasts of non-thermal radio waves, crackling like static from an untuned cosmic radio. Unlike the thermal emissions produced by the sun's scorching plasma, these bursts arise from something far more exotic: electrons accelerated to nearly light speed, spiraling wildly around magnetic fields in ways that shouldn't be possible under normal solar conditions. Take the events captured by the Carl G. Jansky Very Large Array in 2020. While observing a relatively calm region of the Sun, astronomers detected a series of millisecond bursts at frequencies between 1 and 2 GHz, signals so fleeting they'd have been missed by older telescopes. What made them extraordinary was their brightness temperature, a measure of energy output that far exceeded anything thermal processes could explain. Imagine a lightning bolt flashing 10 times hotter than the Sun's surface, crammed into a space no larger than a city. That's the scale of energy we're talking about, concentrated into radio waves that flicker out almost before they're detected. So what's powering these eruptions? One leading theory points to magnetic reconnection, a process where tangled solar field lines snap and realign, unleashing colossal energy. But here's the puzzle. Standard reconnection models can't account for the sheer intensity or the rapid timescales of these bursts. Some researchers speculate they might involve nanoflares, tiny, hypothetical explosions too small to see directly, but collectively capable of heating the Sun's corona to millions of degrees. Others wonder if plasma instabilities like turbulence in the solar atmosphere could be whipping electrons into frenzies, turning regions of the Sun into natural particle accelerators. The implications stretch far beyond solar physics. If these bursts are indeed signatures of unknown acceleration mechanisms, they could reshape our understanding of how cosmic rays, high-energy particles raining down from space, are born. Even more tantalizing is their potential link to similar phenomena observed on distant stars. Red dwarfs, for instance, frequently unleash superflares accompanied by strange radio emissions, and decoding the Sun's bursts might offer clues to these stellar tantrums. Yet for all their mystery, these radio bursts hold a practical warning. Their unpredictable nature poses risks to satellites and communication systems which rely on stable solar behavior. A powerful enough burst aimed at Earth could scramble GPS signals or knock out power grids, a reminder that even our seemingly familiar star still has surprises up its sleeve. The more we learn, the clearer it becomes. The sun isn't just a glowing orb in the sky. It's a laboratory for the universe's most extreme physics, broadcasting secrets in bursts of static we're only beginning to decode. For decades, scientists hunted for the cosmic factories producing the universe's most elusive particles, neutrinos, those ghostly subatomic entities that pass through planets like shadows through a screen. Then, in 2017, an alert lit up telescopes worldwide. An ultra-high-energy neutrino had slammed into the ice cube detector buried deep in Antarctic ice. But this wasn't just any neutrino. It carried a roadmap. Tracing its path back through the cosmos led astronomers to a monstrous blazar 4 billion light-years away, TXS 0506+056, its supermassive black hole spewing jets of plasma straight at Earth. For the first time, we'd linked a single neutrino to a specific source beyond our galaxy, cracking open a new era of multi-messenger astronomy where particles, light, and gravitational waves all serve as cosmic breadcrumbs guiding us to the universe's most violent events. What makes this discovery so groundbreaking isn't just the neutrino's origin story, it's what it reveals about the chaotic engines powering blazars. Picture a supermassive black hole devouring entire stars, its accretion disk glowing white-hot as magnetic fields twist plasma into focused beams traveling near light speed. These jets act as natural particle accelerators, far more powerful than anything on Earth, capable of hurling protons and other charged particles across the cosmos. When those particles collide with interstellar gas or light, they can spawn neutrinos, neutral, nearly massless particles that, unlike their charged cousins, travel unimpeded through magnetic fields, carrying pristine information about their birthplace. The neutrino from TXS 0506+056 wasn't a lone wanderer. IceCube's archives revealed a flare of similar neutrinos from the same direction months earlier, suggesting blazars might be steady producers of these particles, not just one-off factories. This changed everything. For years, the origins of high-energy cosmic rays, charged particles bombarding Earth from deep space, had been a mystery, their paths scrambled by galactic magnetism. But neutrinos, since they ignore magnetic fields, point straight back to their sources. If blazars are neutrino factories, they're likely cosmic ray factories too, solving twin enigmas in one stroke. Skeptics questioned whether a single neutrino could justify such bold claims, but the odds of this being a coincidence were vanishingly small, about 1 in 700. When gamma-ray telescopes like Fermi and MAGIC simultaneously detected a flare from the blazar, the case grew stronger. Here was a smoking gun, light and particles, two different messengers telling the same story. It's like hearing thunder and seeing lightning from the same storm, confirming a shared origin. The implications ripple far beyond astrophysics. Neutrinos are notoriously hard to detect. Trillions pass through your body every second without a trace, yet they're ideal probes for environments too extreme for light to escape. Black holes, neutron stars, and the hearts of galaxies all hide behind veils of dust and plasma, but neutrinos slip through effortlessly. By combining neutrino data with traditional telescopes, we're piecing together a multidimensional map of the universe, one invisible particle at a time. Yet mysteries linger. Why do some blazars flood detectors with neutrinos while others stay quiet? Are there even more powerful sources lurking in uncharted regions of the sky? With upgrades to IceCube and new detectors like KM3NT under the Mediterranean, we're on the verge of answering these questions and perhaps stumbling upon phenomena we haven't even dreamed of yet. The ghost particles have started talking, and if we listen closely, they might just rewrite the story of the cosmos. The universe has a bookkeeping problem, one that's been baffling scientists for decades. When astronomers tally up all the normal matter, the protons, neutrons, and electrons that make up stars, planets, and us, they come up shockingly short. According to our best models, only about half the universe's expected baryonic matter is accounted for, leaving a staggering amount of material missing. This isn't dark matter we're talking about. That's an entirely different enigma. No, this is the stuff we should be able to see, the raw ingredients of galaxies and life itself, playing a cosmic game of hide and seek. So where is it hiding? The leading theory points to the vast thread-like structures known as the cosmic web, an intricate network of gas filaments stretching between galaxies like invisible bridges. Picture the universe as a sponge, its holes filled with galaxies, while the porous material in between holds the missing matter in the form of diffuse, superheated plasma. Detecting this gas is devilishly hard because it's too hot to emit visible light but too thin to block background radiation. It's like trying to spot fog in a pitch-black room with only a flashlight. Recent breakthroughs, though, are shining light into that darkness. In 2017, astronomers using the European Space Agency's XMM Newton telescope finally spotted traces of this elusive matter by observing how it absorbed X-rays from distant quasars, the brilliant beacons powered by supermassive black holes. The absorption patterns revealed oxygen ions in the cosmic web, their fingerprints confirming that at least some of the missing baryons are indeed lurking in these intergalactic tendrils. Even more compelling, studies of the cosmic microwave background, the afterglow of the Big Bang, show distortions consistent with warm gas permeating the spaces between galaxy clusters, further narrowing the search. But the cosmic web isn't the only suspect. Some of the missing matter might be hiding in plain sight, camouflaged as ultra-faint gas clouds skirting the edges of galaxies. Others speculate it could be locked in rogue planets or brown dwarfs drifting unseen through interstellar space. Then there's the wild card. What if a fraction of these baryons have been blasted into intergalactic space by supernova explosions or black hole jets, scattered so far and wide they've effectively vanished from our detection methods? The stakes here are higher than just balancing the universe's ledger. Finding this missing matter is key to understanding how galaxies form and evolve. If half the universe's normal material is floating in these hard-to-see reservoirs, it means our models of cosmic structure might need serious tweaking. It's like trying to bake a cake while half your flour is secretly stashed in the cupboard. You'll never get the recipe right until you account for every ingredient. New telescopes and techniques are rising to the challenge. The upcoming Athena X-ray Observatory, set to launch in the 2030s, will map the cosmic web in unprecedented detail, while radio arrays like the Square Kilometre Array could detect faint whispers of hydrogen gas threading the voids. With every observation, we're piecing together a more complete picture of the universe's hidden scaffolding, one that might finally explain where all that missing matter went. The real lesson here: the cosmos is full of gaps, not just in space but in our understanding, and sometimes the most profound discoveries come from chasing what isn't there until suddenly, against all odds, it is. Among all the strange signals and cosmic coincidences we've explored, none has rattled our fundamental understanding of the universe quite like the so-called axis of evil. This isn't some apocalyptic prophecy. It's a chilling pattern hidden in the cosmic microwave background, the afterglow of the Big Bang itself. When scientists mapped the CMB's temperature fluctuations, they expected randomness, tiny variations scattered like confetti across the sky. What they found instead was something far more unsettling. The fluctuations seemed to align along a specific axis, as if the universe had quietly drawn a line in the cosmic sand. This discovery sent shockwaves through cosmology because it defies one of the field's most sacred principles, the cosmological principle, which states that the universe should look roughly the same in all directions on large scales. No preferred direction, no cosmic up or down. Yet here we are, staring at a CMB map where hot and cold spots appear to whisper about an invisible structure spanning the cosmos. The name Axis of Evil was coined half-jokingly, but the implications are deadly serious. If this alignment is real, and not just a trick of statistics, it could mean our universe isn't as uniform or as random as we've assumed for centuries. Skeptics argue this might be the mother of all coincidences. After all, when you're analyzing something as subtle as microwave fluctuations from 14 billion years ago, noise and statistical quirks are inevitable. Some researchers have crunched the numbers and concluded there's a 1 in 100 chance the alignment is pure happenstance, unlikely, but not impossible. Others have pointed to potential biases in how we process SETI data, suggesting our own Milky Way's magnetic fields or even satellite calibration issues could be imprinting false patterns on the observations. Yet the axis refuses to fade quietly into the background. Independent analyzers using different telescopes and techniques keep finding hints of the same alignment, like a ghost that won't stay buried. The most compelling evidence comes from Planck, the European Space Agency's ultra-precise CMB mapper, which not only confirmed the anomaly but revealed secondary oddities. Certain fluctuations appear slightly stronger along the controversial axis, as if space itself has a grain to it like cosmic wood. Theories attempting to explain this range from the conservative to the revolutionary. On the tame end, some propose our local galactic neighborhood might be tugging on the CMB in ways we don't fully understand, like a pebble distorting a pond's surface. More radical ideas suggest the axis could be a bruise from a collision with another universe during inflation, a multiverse scar left behind as our cosmic bubble brushed against another. Then there's the truly mind-bending possibility that the universe isn't infinite and isotropic as we thought, but has an inherent structure or rotation we've been blind to all along. What makes the axis of evil so unnerving isn't just its existence, it's the way it exposes how much we still don't grasp about the cosmos. The CMB is supposed to be our Rosetta Stone for decoding the universe's origins, a snapshot of its infancy. If even this foundational dataset contains puzzles we can't solve, what else might we be missing? Every new generation of telescopes brings us closer to answering that question, peeling back layer after layer of cosmic mystery. And whether the axis ultimately proves to be a fluke or a paradigm-shifting clue, one thing's certain: the universe loves keeping us on our toes, from the eerie precision of the wow signal to the haunting alignment of the axis of evil. These 25 enigmatic signals have done more than just puzzle scientists. They've rewritten the playbook of astrophysics. Each one, whether a fleeting radio burst or a cosmic structure spanning billions of light years, has forced us to rethink what we know about the universe. Take fast radio bursts. What began as a curious blip in telescope data has blossomed into an entire field of study, revealing neutron stars, black holes, and phenomena we can't yet explain. Or consider Oumuamua, the interstellar visitor that challenged our very definitions of asteroids and comets, proving that the cosmos still holds surprises in our own celestial backyard. Even the false alarms like BLC1's tantalizing near miss have sharpened our tools, teaching us to listen more carefully to the universe's whispers. What ties these mysteries together isn't just their strangeness, but how they've propelled science forward. The hunt for dark matter's radio whispers led to new telescope designs. The search for Dyson sphere candidates expanded our vision of what life's footprint might look like across the galaxy. And the Fermi bubbles, they've turned our own Milky Way into a laboratory for studying black holes on scales we once thought impossible. Every signal, every anomaly is a reminder that the universe isn't just stranger than we imagine, it's stranger than we can imagine. But here's the beauty of it: these aren't just puzzles for scientists in lab coats. They're invitations to wonder, to question, to look up at the night sky and feel that thrill of the unknown. Maybe you're captivated by the repeating rhythm of FRB 180916, or you can't shake the thought of Tabby's star's cosmic dimmer switch. Whatever sparks your curiosity, that's where the next great discovery begins. Because the truth is, we've only scratched the surface. with new telescopes like the James Webb and the Square Kilometre Array coming online. Who knows what signals await us in the static? So here's to the unsolved, the unexplained, and the downright bizarre. Keep asking questions, keep challenging assumptions, and most importantly, keep looking up. The universe is far from done surprising us, and if you've got a favorite cosmic mystery or a theory about what's really behind these signals, drop it in the comments. Let's keep the conversation as boundless as the cosmos itself. Don't forget to subscribe and hit that notification bell because the next big discovery could be just one video away. Until then, stay curious and keep exploring.